Hello Calculus and welcome to 10.1. We will be doing our functions of several variables. You will need a calculator to do this. We will be doing a lot of applications, so I hope you enjoy it. And let's have some fun. All right, so we're going to solve differential equations. We've done this already. So it's just kind of a review. We're going to talk about a general solution. We're going to separate variables. This should be new to us. A logistics growth, which actually requires a higher calculator than you use. We'll be doing just a little bit with this. And equilibrium points. Okay, the first part is just a review. Remember, the derivative of y of x is equal to g of x. So in order to find y, you have to take the antiderivative. Nothing unusual. Now let's start off with our story problem. We have a population, P is what population is. A flock of birds is growing exponentially. So our equation is given to us. We have a derivative with respect to time. So as time goes up, population goes up. So we have to figure out what this means. T is time in years. Here it says P in terms of T were 20 birds in the flock initially. This is a point. That means when I have no time, I started off with 20 birds, or P of 0 equals 20. We have to understand this. So first we do our antiderivative, remembering the antiderivative of e to the 0.05t is itself divided by the derivative of the exponent, which is 0.05. We just divide the 20 by the 0.05, and our new equation is here. Now, in order to solve, we have to plug in our initial value, which is 20 when we have no time. Anything to the 0 power is 1, so that just cancels out. Subtract it over, and c is our negative 380, and we plug that in. Okay, I would like you to pause the video and try the one on the next page. Make sure you do that. Okay, we have to find the general solution of 1 and 8. So this time the point they give us is 1, 8. So what happens? So we go through here and we look at, and we've got a derivative of y. You should have first recognized that this is in the wrong spot and added it to the other side. We need to take the antiderivative of both of these. Well, when we do so, this is like separating them out, right? So 2x dx, well, we just know that's x squared divided by 2, which brings us down to here. You have to recognize this one. You use your x squared plus 3, which means you do use the 2x plus dx, which we have. So we got the 2x dx, so we can now do the problem. So now you do the antiderivative of the x squared plus 3 to the negative 1/2. So this is u to the negative 1/2 du. Well, u to the negative 1/2, you add the 1, giving us 1/2, dividing by 1/2 or multiplying by 2. So this is where we got the 2. We replaced u with x squared plus 3 to the 1/2 plus c. Now we need to plug in our point, which is 1 and 8. So 8, 1 squared, 2, 1 squared plus 3 to the 1/2 power plus c. Calculates the math, and we find out that c is 3, giving you your final equation of x squared plus 2 times, and you could have left this x to the 1/2 or put it in the square root. I do not care, and c is the 3. Not bad, huh? All right, let's see if we can get a little bit more challenging here. This is called separation of variables. I have a y and an x squared. Well, this means I want to put the dy with the y variables and the dx with the x variables. So I need to multiply the dx up, is what we've done here. So I've separated them out. We've got the y and the dy together, the x squared and the dx together. Now we just do the antiderivative of both sides. Y squared is y squared over 2. X squared is x cubed over 3. Don't forget your plus c. Now we need to solve for y, but we have to be a little careful. So I multiply everybody by 2, but I can't finish solving this because I do not know from this equation if y is positive or negative, and I do not want two equations. So we stop at the y squared. Remember, c is just a constant, so if I multiply it by 2, it is still just a constant. So 2c just becomes c with the 2 incorporated in. And we're done. All right, pause and try yours. Okay, I hope you did well. First thing you should have said is, hey, this y squared is in the wrong place, so I need to multiply him up to go with my y. So I've got y squared dy. Now the x's are on this side, and I multiply up here by the dx, so the x's are together. Now, this side is not so bad, that's just the integral, but this one here is a little messy. So in order to do this, since this is a monomial in the bottom, I divide each. X squared divided by x is x. 1 over x is just 1 over x. Well, y cubed over 3, we've done this a lot. There is a plus c, but I just need it on one side, so I just left it with the x since I'm solving for the y. Okay, antiderivative of x is x squared divided by 2. And antiderivative of 1 over x is the natural log of x plus c. Multiply everybody through, I forgot my 2 over here too, by 3. So we got 3x squared, 3 natural log. Remember, a constant times 3 is still just a constant. Here, I do not have to stop because when I take the cube root here, if it's positive or negative, it will stay positive or negative. So you're taking the cube root of this entire thing, which is just the entire thing to the 1/3 power. It does not matter which way you leave it. I hope you did a good job. All right, next, let's see if we can remember our natural logs and our e's. Oh, this looks funny. That hopefully is not on yours. This actually just should not be here, or this one here. Just ignore those. We should rewrite. Okay, we have the derivative of a with respect to t, a constant times a, which means I have to get the a's together. And usually we like to put the constant with the t just because it's easier to use. So to get the a's together, I must divide by a. So we're dividing by a here. We're dividing by a here. The dt needs to move up, so we multiplied by t. This is how we got here. Now, this should have said the integral of 1 over a times the derivative with respect to a equals the integral of a constant, okay, with respect to t. Well, now 1 over a we know is the natural log of a. The constant's just a number, so we must add our t to it and plus c on one side. Now to get the a out, in order to get rid of a natural log, we use e. I'm hoping you remember. So we have to take e to the natural log of a, and then e to this entire thing becomes his power. Now when we do this, these cancel and we get a. Here you have to remember your rule of exponents. When you're adding, you're really multiplying e, right? Because if I did x squared times x cubed, that is x to the 5th or x to 2 plus 5. So we just went backwards. We said my addition means I'm multiplying like bases. That's how we got here. E to the c again is just a constant, and we renamed it m. It's actually what we use in the growth and decay, which is fine. The k is now your constant of variation, and we've used those before. I hope you remember them. Okay, let's continue on. Now let's apply this a little bit. I have 4,000 mountain goats in reserve. It follows the growth rate is proportional to how close the population is to the max. With a growth rate of 20%, there are currently 1,000 goats. All right, they give us this. So this is the equation we have to use. I have to separate out my variables again. So the dt comes up, but the n minus y is in parentheses, so that entire thing goes to the denominator when I divide. Again, this should be gone. So I have to take the integral of both sides. Well, recognize that this is the integral of n minus y to the negative 1 dy. Well, anything to the negative 1 is the natural log of n minus y, but then I got to take it times the derivative of the inside divided, which is negative 1, and that's where this came from. Again, this is just k, so that's kt, and we put our c over here. Now we must solve, but this negative 1 must go away first, so we divide everybody by the negative 1, so that means we change everyone's sign. Again, we take everybody to the e power in order to eliminate the natural log. We're getting closer, so we have n minus y. Now, using our rule of exponents, I made this here a plus a negative c. So it's negative kt e to the negative c. This, again, is just a variable. So that became our m. Here is our constant of variation. This time it is negative, minus n. Get y positive, so we multiply everybody by a negative. Okay, we have our equation. Now we must use this equation. So I know when I have 0 time, I have 1,000 goats. So 0 in for time, 1,000 in for goats. This here again, anything to the 0 power is 1, so that goes away. So I have minus m plus n equals 1,000. I need to solve for m, so I'm going to add him over and subtract the 1,000. There's my equation. Now I'm going to replace this in for my m, and that gives us this equation. So this is just what m equals right here. Nothing too exciting. I know that when I have a 20% growth, I have a 4,000 goats are in. So I plug 4,000 in for the goats. I plug in a 20%, that's my constant of variation, and we just solve this. So we plug this into our calculator, that gives us negative 3,000 on the inside, plus our 4,000 on the outside. Now I have a 20% growth. I want to know how many goats I have after 5 years, which means now I replace the t with 5, and I have 2,896 goats. Okay, I would like you to pause and do yours. Okay, I hope you practiced the first part. This was identical to page 1, but it's good practice to do your integrals, correct? This here was also identical. So all you had to really do is plug in the 0.15, the 5 years, and the 6,000 goats, and you should have gotten 3,638. If you did not practice this, go back and do so you get your integrals in there correct and your absolute values and your natural logs. All right, a logistics model actually requires the calculators that I don't let you use yet, but we will do a little bit with them just so you understand. They always have a limiting factor, and up here, this here is an asymptote. It's what it approaches but doesn't quite reach, and that's our limiting factor. We will use that quite a bit. So it's usually 0 here, and your other asymptote is down here. So there's 2 asymptotes on the logistics growth model. Okay, the limit of the function, there is still a k, or a constant of variation. And we will use, since we can't use technology, we don't do a lot with this. But let's do a little bit here. Okay, so all you have to know is n is your limiting growth function. That's what I need you to remember. So if I give you an equation, the top number is your asymptote. Okay, an equilibrium point is, this occurs when the function is set equal to 0. All right, in the logistics model, y equals 0 or it equals n, because we have the top or the 0 bottom. So we look at this, we know it's stable, or a stable point, if when it nears the equilibrium point, it moves closer to the point, so from both sides. It's unstable if it moves away, semi-stable if one moves away and one moves towards. So let's see if we get you some examples of this. This is going to be my equation. We can't do a ton with this because of the model, so we just set each of these equal to 0, so it will be done for you basically. So you set this one equal to 0, this one, and this one, and we get 3 points, 0, 1, and 2. All right, so now we draw out our number line, just like we did when we did maxes and mins, and we plug in 0, 1, and 2. We plug in our original equation into our table mode, so you're plugging in the 1, let's back up, you're plugging this into the table mode on the calculator. All right, just like before, nothing unusual here. Now we're going to plug in 1 point on each side of our equilibrium point. So negative 0.5, I chose 0.5, 1.5, and 2.5. It really doesn't matter. When you plugged in the negative 0.5, I got negative 3.56. 0.5 is 0.64. 1.5 is 2.4. Positive is all we truly need. And 2.5 was a negative 165. So I had a negative, a positive, and a negative. So negative is going in this direction. Positive is the positive direction, negative direction. Now we're looking at what the points do. So when you look here, their arrows are going away from each other. Since they are away from each other, 0 is an unstable point. Okay, when we look at our next section, This time the arrows are, one's going towards the point and one's going away from the point. So one is a semi-stable. Your book, unfortunately, in the back doesn't use semi-stable, even though it should. Just realize some of those answers may not be correct. And then here, when we look at 2, we have one arrow going, they are both going towards 2, which means 2 is a very stable point. So we like that. And that's all you're looking for, is stable and unstable. So now, whoops, sorry, pause and do yours. Okay, when you plug that into your calculator, you should have gotten your number line. You should have had -2, -1, and +2, because the square root of 4 is positive and -2, and this was -1. Okay, when you plugged in your thing, I don't care what you used. I used -3, -1.5, 0, and 3. When I plug those in, here I got 10, or a positive number. Here I got -1 or -0.895, or a negative number. Here I got 4, or a positive number. And at 3 I got -20, or a negative number. So now when we draw our things in, this is positive, so it's going this direction. Negative is this direction. Positive and negative. Which means when you look at this, -2, the arrows are going towards, so -2 is a stable point. When you look at -1, I have both going away, which means -1 is unstable. Now when you look at a +2, you're looking at these two arrows, both are going towards 2, so 2 again is stable. All right, good luck on your homework. I hope you do well, and make sure you post questions if you have any.